In the last video, we took a look at the gravitational force, and we also realized that the term weight does not have a universally agreed upon definition, and realized that that means that we have to figure out when a problem asks about weight, whether we are looking at the normal force or gravity. Okay, so here I want to talk about how to use Newton's second law to help us analyze force problems, and I figure it's probably best to just kind of do this by way of example. So let's say we've got some sort of a three-way tug of war here. So we've got some object of unknown mass, and we've got three people who are tugging on it like so. Now we know that this first person is pulling straight to the left with 100 newtons. We know this second person is pulling straight to the right with 100 newtons. What we want to know is how hard is this person pulling, so that'd be the tension, and also what angle relative to the horizontal should we be pulling at. And we know they'll be south of east just from common sense, but how many degrees? So let's go ahead and figure that one out. So the idea here, so since this is a tug of war, one of the additional bits of information we get is that the acceleration has to be 0. Now, I tend to stick a little arrow over a 0 just to still remind me that it's technically a vector. But yeah, so the acceleration is 0 because it's a tug of war. We haven't gotten anywhere yet. So now let's go and draw, so we can go ahead and do a force identification diagram for this. And we are just cutting through 3 ropes. So we'll have 3 forces due to tension. So let's draw them in, and let's try to be reasonably accurate about it. So this will be T1 is equal to 100 newtons. This is T2, also equal to 100 newtons. Now we know, since the acceleration is 0, we know the forces have to add up to 0. So if I were to just do the parallelogram rule to add these two, I'd get something like this. I'd have to add in something that would cancel that. So I know that T3 has to be pointing this way. And like I say, again, we don't know the magnitude or the angle. But what we can do is we can go ahead and start writing down Newton's second law of motion for this. So A would equal F net over M. Usually we'll end up writing F net equals MA here. So what we're going to want to do is we're going to want to break this into components. But before we do that, let's just write a nice general vector expression for this. So this will be T1 plus T2 plus T3 equals MA, and we already said that A was 0, and it's always fine to stick 0 in whenever you've got it. So what we've got is the 3 forces have to add up, have to cancel up when I vector add them. All right, now that we've done that, let's go break these up into components going to the land of X and the land of Y. So looking at my free body diagram, I can go ahead and drop in a coordinate system to help me think about this. So this would be my plus, there we go. This would be my plus x direction. That'd be my plus y direction, unless that's the default, unless specify otherwise. So here, what we're going to be looking at is, if I take the x component of this equation, it's going to be t1x plus t2x plus t3x equals 0. All right, let's come up with expressions for each of these. So t1, if I look at it, I see that it's pointing completely along the x-axis. So since 100% of it's along the x-axis, all we have to do is figure out, is it pointing right or left? And here I look at it, it's pointing left. So for t1x, I can just write minus t1, because the whole thing is pointing left, and the minus sign, because the whole thing is in the x-axis, and the minus sign means to the left. Similarly, I look at t2 and I see the whole thing points vertically. So the x component is going to be 0. This is going to leave me with find the x component for t3. Let's just highlight that out. So this piece here will be t3x. This piece here will be t3y for when we get there. So to write down t3x, we can use our trig and realize that t3 is the hypotenuse, t3x is the adjacent. So this would have to be equal to t3 cosine theta. And we keep a plus sign because it's pointing right-ish. Okay. Now let's go ahead and go over to the land of y and analyze the y components of the forces. So we start the same place. t1y plus t2y plus t3y equals 0. Now if I look at t1y, well, t1 is pointing entirely along the x-axis, so it has no piece in y. So that would be 0. T2 lies entirely along the y-axis, and so all we have to do is worry about direction. It's pointing up, so we just say plus T2, because the whole thing is along the y-axis, and again the plus sign is because it's pointing up. So for T3y, we can see that T3 is pointing down-ish, so that's going to pick me up a minus sign. And this is the opposite, so that would be a sign. So T3 sine theta equals 0. Okie dokie. And sorry, here I should have also been saying equals 0. And I should probably make that piece blue. All right. So now what we can look at either of these and get our T3. So because we happen to know both T1 and T2 in this case. So the problem's overspecified. So we could have gone so far as to just say, what is T2 equal to? But let's just go with this for now. So here, T3 cosine theta would equal T1, just saying T1 to both sides. T3, oh sorry, we don't know theta yet, my bad. So because we don't know theta, what we're going to have to do is solve one of these for T3, stick it into the other one. That will eliminate the T3, and then will give us an expression for our angle. So let's do that. My apologies there. So let's start with this one. We'll say T3 cosine theta equals T1, just saying T1 to both sides. So T3 equals T1 over cosine theta. I can now take that and stick it in over here for T3. So here I'll get T2, which I know is equal to T1 over cosine theta times the sine of theta equals 0. Oh, sorry, my bad there. That should be a minus sign. All right. Now we remember that sine over cosine is tangent, so I could just as easily write this as T2 minus T1 tan theta equals 0. And so I can go ahead and add T1 tan theta to both sides. So it equals T2 or tan theta equals T2 over T1. All right. To get theta by itself, I need to take the arctangent of both sides. So the arctangent of the tangent of theta is theta, leaving me with the arctangent of T2 over T1. All right, but we can figure that out. So theta will be the arctangent of 100 newtons over 100 newtons. Cancel, cancel. Remember, anytime there's a trig function or an inverse trig function involved, the units better all cancel out. And so this is the arctangent of 1, which turns out to be 45 degrees. Great. Now that we've got that, we can take that answer and stick it into either of these, but since that one's just sitting right out there, let's use it. So this will give me T3 equals T1 over cos theta, so that would be 100 newtons over the cosine of 45 degrees, which will work out to be 141 newtons. So it turns out that our third person, to keep the tug of war fair, is going to have to pull down and to the right at 141 newtons, 45 degrees south of east. So this is an example. It's called a statics problem. That's where the acceleration happened to be 0. Let's take a look at a case where the acceleration isn't 0. So let's say we've got a 10 kilogram weight. That is sitting on a scale. And the whole thing is sitting in an elevator car. Now the elevator is going up, so we know the velocity is up, but it's slowing down at a rate of 2 meters per second per second. So that means that the acceleration is pointing down. So what we want to know is, what is the number on the scale? Well, the number on the scale, remember, is the normal force. So let's go ahead and start by drawing a force identification diagram for the weight. So what we've got is the normal force of the scale pointing up. That's it for contact forces. So we've got the gravitational force of the Earth pulling down on the weight. Notice I'm not drawing them equal. This is because I know that since it's accelerating downward, I already know the net force has to end up ultimately pointing down. Okay, so there's our free body diagram. We can go ahead and pick a coordinate system. So plus x plus y. And then let's go ahead and start expressing Newton's second law of motion. So we'll just say F net equals ma. And so F net, remember, is this vector sum of all the forces. So this will be n plus Fg as vectors equals ma. All right. Now here we'll want, when we go to the land of x, there's nothing useful here. And this is because all of the action is happening in y. So let's go to the land of y. So the normal force is acting up. So, well, let's just say n sub y plus fg y equals m ay. And now let's start substituting those things in. So the y component of the normal force is pointing up, and it's entirely along the y, so we can just write n. Gravity is also entirely along the y, so no sines or cosines, but it's pointing entirely down, so we need to put in a minus sign, minus fg. So equal m. The acceleration is pointing entirely down, so again that'd be minus a, like that. All right, so rearranging a bit, we can write that the normal force will be equal to the force of gravity. If I multiply that minus sign through, this becomes minus ma. And from our understanding of gravity, we can say this is mg minus ma. We can group the m's. So we're left with m times g minus a. So my normal force will be equal to, my mass we said was 10 kilograms. This will be 9.8 newtons per kilogram for the gravitational field strength, minus 2 meters per second squared. Now the units are compatible because remember, newtons per kilogram have exactly the same thing as writing meters per second dimensionally. I just do this to remember that this is a gravitational field strength, which is not the same thing as our acceleration, which is 2 meters per second squared. Anyway, you go ahead and multiply it all through, you get 78 newtons. So the scale reads less than what the force of gravity would read. And this should square with your experience with elevators. When you come to a stop on the floor, you guys feel just a little light on your feet. That's why. Alrighty, I'll go ahead, have a good one, and I'll catch you in the next one.